All right, guys, good morning or good afternoon if you're one of my afternoon classes. Today we're going to talk about predicting bonds based on electronegativity differences. So make sure that you've picked up both the handouts from the front table and that you have your Chromebook and a pencil. Okay, these questions in the Lumio, I want you to kind of click along in the Lumio with me if you can in a separate tab, because I'll have some stopping points as we go through the lesson. So this first slide, these are your warm-up questions. I want you to pause this video right here and answer these warm-up questions in your notebook. The next slide in the Lumio, I typed out just a quick little answer key to these warm-up questions, just so you can kind of make sure that you're on the right track. You don't have to have everything word for word, but you should have something along these lines. If you don't, make sure that you correct it in your notebook. So yesterday we talked about the differences between covalent and ionic compounds. Covalent compounds are also known as molecular compounds. These are held together by covalent bonds where we are sharing electrons in between two or more nonmetals. Ionic compounds or ionic bonds are when a metal transfers its electrons to a nonmetal. These bonds, within covalent bonds, we can have what are called polar and nonpolar covalent bonds. The way that we determine if it's polar or nonpolar, it's all going to be based on the electronegativity differences. So kind of reviewing from last unit, electronegativity is an atom's ability to attract electrons from another element. So if there's a greater difference, the compound would be more polar. If there's a lesser difference, the compound would be nonpolar. So we're going to look at some visuals and we're going to look at a simulation to kind of explore those differences. Okay, so on your handout that has the questions on it, you are going to, I don't know why it's not showing up on here. You're going to look at this PhET simulation. It's on slide 7 in the Lumio. So that's why I kind of wanted you to follow along with me as I talk through this stuff. But take about 5 to 10 minutes. It shouldn't take you longer than that to answer the things that are on your handout. So when you open up your PhET, you're going to click on 2 atoms. Give it a second to load. We're going to click on 2 atoms. And then I'm going to highlight some of the things that I want you to make sure that you click on your end as well. So on this right-hand side where it says view, we want to make sure that we have bond dipole checked. That's defaulted. But we also want to check partial charges and bond character. Partial charges are going to show you if there's a positive and a negative end of the molecule. Bond character is going to tell you if it's more covalent or more ionic. And then down here underneath surface, check electrostatic potential. Blue means it's more positive, red means it's more negative. So you're going to play around with the electronegativity differences down here at the bottom. And the sheet that you have in front of you will kind of guide you through what to click and what to write down and what kind of things to look for. So I think it says to leave electronegativity for atom A alone and play with atom B, and you're going to kind of jot down some things that you notice. Okay, so go ahead and pause this video here and work on that PhET simulation, answer those questions. Okay, so again, 3 types of bonds. Today we're going to talk about ionic and covalent, but within covalent we also have polar covalent and nonpolar covalent. So that's the new piece that we're learning today. Bonding between atoms is sometimes kind of in between ionic and covalent. Electronegativity is going to determine the polarity of a molecule. So again, it's the atom's ability to attract electrons. Remember your trend for electronegativity. Your noble gases are not electronegative. They do not attract or give away any electrons. They don't react at all. Your most electronegative element is up here, fluorine. These are all higher. And then when you get down here in your metals, especially your alkali and alkaline earth metals, down at the bottom of those groups are the least electronegative. The difference in electronegativity determines the type of bond that will be formed between 2 elements. In general, elements that are closer together on the periodic table are going to be more nonpolar. There's not a big difference in electronegativity. So they're kind of sharing the electrons equally. Elements that are farther apart have different electronegativity values and are going to be more polar. The ultimate polar bond, meaning the most polar that you can get, is an ionic bond, because the differences in electronegativities are so great, because you have a metal and or I guess your side would be metals and non-metals. Because you have a metal and a non-metal that are bonding, the electronegativity values are very different. So like over here, if I have this metal and this non-metal bonding, big difference in electronegativity would be ionic. With covalent, the farther apart you get within your nonmetals makes it more polar. The closer you are would be more nonpolar. Okay, so we're going to look at the periodic table in just a second and how to predict polarity using just that. Just as kind of a visual, nonpolar covalent means that the bonding electrons are shared equally in the middle between these two atoms, okay? Polar covalent is when the bonding electrons are shared unequally. So this polar covalent bond right here, if you look at partial charges, your positive and negative, this one over here is pulling in the electrons a lot more strongly from this end. Whereas in this molecule, they're pulling equally and they're sharing pretty equally, they're evenly distributed. But this guy right here is pulling the electrons in more strongly. Okay, this is a really good visual or a good analogy for polarity is tug of war. When you have a game of tug of war and the people on either side of the rope are both equally as strong and they're pulling equally, that's what we would consider a nonpolar covalent bond. So when your atoms are pulling the electrons equally, nonpolar. I like to say nonpolar, no winner when you think of tug of war, because they're pulling equally, it's a tie, nobody's gonna win. With a polar covalent bond, you can see that this group right here in red is pulling the tug of war, the flag is moved over the line. These guys over here in blue aren't pulling as strongly. They're a little bit weaker, but it's not so weak that they've pulled the people over the line. Ionic bonds down here, the difference between polar covalent and ionic bonds, the red group is so much stronger that they're actually pulling the purple people across the line as well. Okay, so if you've ever played a game of tug of war and you've played a game against someone that's pretty even to you and there's no winner, that would be nonpolar. If you're a little bit stronger, that's polar. If you were way stronger, that would be ionic. Okay, and again, of course, we know that ionic is between metal and nonmetal, and both polar covalent and nonpolar covalent are still between nonmetal and nonmetal. So when we're looking at the periodic table, we can actually just glance at the locations of elements on the periodic table to see if they're going to be more polar or more nonpolar, depending on how far apart they are. So we know our general trend for electronegativity is that noble gases don't react, and our general trend, it increases up and to the right towards fluorine, okay? So if I'm trying to determine whether a compound is polar or nonpolar, or whether a bond is polar or nonpolar just based on location on the periodic table, I want you to have your periodic table in front of you and use your fingers and physically touch where these two elements are on the periodic table. The closer your fingers are, the less polar or the more nonpolar. The farther apart your fingers get, the more polar the bond is. Okay, so if we're looking at chlorine and chlorine, I want you to take your fingers and touch chlorine and chlorine. Well, that's the same element. So there is no difference in the electronegativity value there. So that is the most nonpolar that you can get. So chlorine and chlorine, nonpolar covalent. Nitrogen and oxygen. Here's nitrogen, here's oxygen. Okay, those are still really close to each other, even though it's not the exact same element. They're very close to each other. They're both nonmetals, so we know it's covalent, but because they have such similar electronegativity values, I think my thing got crooked, because they have such similar electronegativity values, because they're so close, this would also be considered nonpolar covalent. Okay, the next one we have magnesium and bromine. These are really far apart, so this means that they're going to be extremely polar. They're not only very polar, but look at the types of elements that are in this bond. We have magnesium, which is a metal, bromine, which is a nonmetal. These would be considered ionic. And I'm going to make a note here that that is the most polar. Okay. The next one's sulfur and oxygen. Again, both nonmetals, so they're very close to each other. This would be considered, again, nonpolar covalent. And then the last one, rubidium and fluorine. Rubidium and fluorine, if you touch those two on your periodic table, again, we have a metal and a nonmetal. This would be ionic, which again is the most polar. My S kind of looks like an 8 here. Most polar. Okay. Now we're going to look at another types of bonds. We're going to see which one would be more polar of the two options. So the first one is carbon and oxygen, or silicon and oxygen. Okay, carbon and oxygen, silicon and oxygen. So really you're looking for which one is further away. So the most polar between these two would be silicon. Silicon's slightly farther from oxygen than carbon is. Okay, the next one we have oxygen and fluorine, or oxygen and chlorine. Again, which one would have a bigger difference? Oxygen and fluorine side by side, pretty similar. Oxygen and chlorine are kind of diagonal with each other. They're still close, but chlorine is a little bit farther, so chlorine would be slightly more polar. And then we have carbon and hydrogen, or silicon and hydrogen. Okay, again, we're looking for which one is farther away. So carbon and silicon. Silicon's going to be slightly farther away, so more polar. Now we're going to look at electronegativity values. You do not need to memorize these numbers. What you do need to know, however, is this piece right here. Okay? These are the electronegativity values for all of these elements on the periodic table. When we're determining polarity, we look at the difference in the electronegativities of the two elements. So for example, if I have, let's see, carbon and chlorine bonding with each other, okay, I'm gonna look and find the values for carbon and chlorine to determine if it's polar covalent, nonpolar covalent, or ionic. We know that this would be covalent because it's nonmetals. If it were ionic, the difference between those values would be greater than 1.7. But we're looking at covalent, so polar or nonpolar. If it's polar, the difference is between 0.4 and 1.7. If it's nonpolar, the difference is between 0 and 0.3. So I would take the value for chlorine, because chlorine's bigger, which is 3.0, and subtract 2.5, and I have a difference of 0.5. That puts us in this polar covalent category. Okay, so that's just one example. Let's work some more. Okay, lithium to fluorine. Here's lithium, 1.0, and fluorine is 4.0. So the difference, 4 minus 1, equals 3.0. That's greater than 1.7. This is ionic. And I can also tell that it's ionic because lithium is a metal and fluorine is a nonmetal. The next one, hydrogen and oxygen. Hydrogen is 2.1. Oxygen is 3.5. So if I find the difference, 3.5 minus 2.1 equals 1.4. So a difference of 1.4 would make this polar covalent. The last one, chlorine to chlorine, it's the same element. So chlorine to chlorine, they are both 3.0. So the difference is 0. 3 minus 3 is 0, which would make this nonpolar covalent. Okay, let's work some more examples. The first one is KBr. We can be able to tell whether it's going to be ionic or covalent just by looking at the elements. If it's covalent, that's where we're going to determine if it's polar or nonpolar. For KBr, we should be able to identify, hey, potassium is a metal and bromine is a nonmetal. That automatically makes this ionic. But if we want to look at the differences in electronegativity, bromine is 2.8, potassium is 0.8, so these have a difference of 2.0, which makes it ionic. Okay, the next one is CH4. Carbon is 2.5, hydrogen is 2.1. Now, whenever you have subscripts in your compound, we don't multiply the value times the subscript, okay? The only time the subscript matters when you're looking at electronegativity differences is if there's only one element, like this last example down here. So I'll tell you what to do with that one here in just a minute. But for all these other ones, CH4 and H2O, we are ignoring the subscripts, okay? So for CH4, carbon is 2.5, hydrogen is 2.1. We find the difference, which is 0.4. That makes this polar covalent. Magnesium oxide. Again, we've got a metal and a nonmetal. That automatically makes this ionic. But if we want to look at the difference, oxygen is 3.5, magnesium is 1.2. So they have a difference of 2.3. Okay, let's look at H2O or water. I don't know why I just erased that. I need it anyway. Again, we are not going to use this subscript here. We're just going to look at the value for hydrogen and for oxygen. Oxygen is 3.5, hydrogen is 2.1. So when we subtract, we get 1.4, and that falls in the polar covalent category. Okay, lastly, we have F2, and here's the only time where the subscript matters is because it's telling us fluorine is bonded to itself. There are 2 fluorine atoms. That's one of your diatomic molecules that you need to have memorized. Okay, so fluorine and fluorine means you have 2 fluorine atoms. So 4.0 minus 4.0 is 0, which is going to fall nonpolar covalent. Okay, this handout I want you to glue into your notebook. This shows you the difference visually with ionic, polar, and nonpolar covalent. It also tells you the electronegativity differences. So with an ionic bond, the electrons are transferred. So you can see these are still kind of 2 separate ions because they're not sharing anything in between them. And then it tells you the electronegativity difference at the bottom. Your polar covalent bond, you have electrons being shared unequally. So if you look at your partial charges here, you have one end that's more electronegative than the other. The electrons are being pulled toward that negative end. Your electronegativity difference is between 0.4 and 1.7. And then lastly, we have nonpolar covalent. There are no poles, okay? That means the electrons are being shared equally in the middle, and you have an electronegativity difference of less than 0.3. I want you to answer this question in your notebook real quick. It says, which pair of atoms could bond to form a polar covalent bond? There is only one correct answer here. Pause this video and answer it, and then we'll talk about it here in just a second. Okay, so if you're following along in the Lumio, in another tab, you can see the explanations here. Lithium and fluorine would not be polar covalent. They are very polar, but because this is a metal and nonmetal, they form an ionic bond. Carbon and fluorine are both nonmetals, which makes it covalent, and they're farther apart on the periodic table. If you look at the electronegativity values, the difference would be 1.5. The next one, oxygen and oxygen. It's the same element bonded to itself. It is covalent, but there is no difference in the electronegativity values, so it would be nonpolar covalent. And then lastly, you had nitrogen and helium. Helium, of course, is a noble gas, and it does not participate in any type of bonding. Okay, your homework for tonight. First off, make sure that you have taken notes over electronegativity differences. You've written the examples down that we worked through, and that you have glued both of these handouts into your notebook. Glued or taped or however you do it. Don't have loose papers flying everywhere, okay? For your homework, you're gonna go and complete the Canvas quiz. And then just a reminder, your ions quiz number 1, which is all of your cation ions, and then your anions through hydroxide. Quiz number 1 is Thursday, October 9th, okay? Thank you all for working hard today. I will be back tomorrow.